You can hear me?
Oh, okay. So hello, everyone. Um, Thanks for coming. And I don't know if someone is connected online. Um, can you hear me? Yeah. So today we have seminar by Zurab, that is a collaborator that has been coming to the ISC last year, and also this year he came several times. We are working together in different topics, and he is coming from the Slovak Academy of Science. And I would just give you a very brief introduction because he probably will explain more later. But the important thing is that I asked him to start with a general introduction of the main topic that he's working on, so then the general audience can understand more or less the background of the science that he's doing. And then at the end, he will present the specifics of the collaboration that we are doing together, and hopefully you will be able to follow. Okay, thank you.
So thank you for coming. Thank you who is online. So today, briefly, just I will speak about the sun, their interior. This is our nearest star. You already know this, and it's vital important to study for us because it's have a huge impact on the Earth, on our lives. So the sun is not the solid body. This is the dynamic plasma sphere, and it's all the layers which it have different consequence or different generation of the energy and transportation it from the core to upper layers in atmosphere, what we call surface. So just to start that, in the center we have core. They are the this hydrogen converts to the helium, and from the nuclear fusion. Then the energy transferred in the transition region, and then to convection zone, and then finally it's appeared on the solar surface. As I told you, so we have core, then we have radiative zone, convection zone, and then comes the solar atmospheres, photosphere, chromosphere, and the corona. Mostly we will concentrate on the chromosphere today, but also it's important to define all these layers, because the not only the event which we observe is not only the event which appear in the atmosphere. It is the it connects to the deeper layers, so all these energetic events are transformed in the deeper layers. So then we have it on the surface. So as a solar physicist, for us, it's important to study all the layers and study the connection between the for example, the convection zone and the upper atmospheres, for example. And the most powerful event in solar core, one of the powerful event is the solar flares. So it is the mostly energetic flares, and sometimes it appears sudden, so it releases energy, and it's connected to the space weather also. So it's really important to study these phenomena. So on the right side, you can see the solar atmosphere. So photosphere, in the photosphere, we see mostly the sunspots. In the chromosphere, the fibrils, then speckles, flares also as ribbons, ribbon flares. And then in the corona, we see all these energetic events like flare, eruption, CME, coronal mass ejection. Mostly, as I told you, the flares are energetic events. The charged particles are ejected outward with high speed. So on the left side, you can see the image, which is taken by the TRACE spacecraft. So the flares in the corona appeared like the bright loops, and you can define these loops, magnetic loops, easily. And on the right side, you can see from the spacecraft the videos which show the few events of this flare. And so again, this is powerful events, and it's important to study it. Yeah. So we have few classifications. So A, B, C, M, and X class. So most powerful are X class flares, and then comes M class flare, and then C class flares. So mostly our work concentrated on C class flare. This is not so energetic flare. It has small influence on Earth, but still it's very important. So just to compare the M or X class, they are rare in solar atmosphere, comparing to the C class flare, but they are much more energetic. So on the other hand, we have a lot of C-class flares, but not so energetic. But the physics is the same, so we will just, if we will understand all the processes, all the dynamics of the flare, what is going there, literally we can have some knowledge about all other classes. Just the energetic will be different. Also, the solar flares are not isolated. It's sometimes connected with CME, with the eruption, which influence on the space weather. So because of that, it's important to study. So we have few for example, several reasons to observe these flares or these events. First, just to drive the physics, how the energy transported from the low layers to upper layers. Then also the physics, how it connects to the space weather, would have impact on the Earth, and then, of course, the sun is our nearest star, and mostly to study all these phenomena, dynamics, we will have some knowledge about the same type G-type stars. So yeah, because of that, it's important to study. So as I told you, it has huge impact on the Earth because of the connection of the CME, because of the throwing these energetic particles in the space. So just to defense ourselves, just to define some perfect, not perfect, at least some model of the, to create some model of the chromosphere, to understand all this physics what is going there. It is vital, important to study the flares. So today mostly we will concentrate in the infrared light. So the spectropolarimetry of C-class flares. So why infrared? Because of the few reasons. First, it's not overcrowded. Then also the spectral lines are sensitive to the magnetic field, and the specific lines can be diagnosed easily. So mostly we use the helium 10813 helium line triplet, which is mostly origin in the chromosphere, with the silicon and calcium and also the sodium, which are mostly the photospheric lines. So in this sense, we have different layers, different atmospheres, so we can easily compare to each other and try to understand what is going there during the flare. So the normally stellar spectroscopy starts with the measure of the intensity of the beam straight light as a function of the wavelengths, but also light can be linear or the circle polarized. So measurement of the polarization, it's vitally important also for us to have just more knowledge about the magnetics, about the magnetic structure, about the 3D or reconstruction of the magnetic fields. So for that, it's easy to just to constrain the geometry from this spectropolarimetry. So we can, so we use the Stokes parameters for that. First Stokes I intensity, then Q and U for the liner polarization, and the V is the circle polarization. So on the right side, you can see the spectrum from our observation, actually, with Q, U, and V. From the special point, there was not so active during in this area, actually. And on the left side, you can see the slit scan with the wavelength on the x-axis. So mostly we observe it in 2023 here in Observatory del Teide with the 1.5 meter GREGOR telescope. So it have two main instruments, GRIS and HiFI. So this observation we are done by agreement with the SolarNet project, and I was the PI of the Observe campaign. So we use the GRIS infrared GREGOR Infrared Spectrograph. We use 1.0, 1.3 microns, and we also use the HiFi, from which we use the calcium H line and TU. Mostly calcium line represent the chromospheric line, and TU is much more photospheric line. Our solar flare, I mean, we observe two solar flares which appeared consecutively next to each other. So first appeared the C4.7 class flare, then C3.5. So here on the zoomed image, you can define these flares from the 7 universal time 7:15 until 2:10. Of course, this is much more broader time. We have less observed time. So, but I mean, the flares were accompanied with the eruption, so you can define it easily here. Then some eruption appear. Because of this event, because also the next slides I will show how the spectrum was look like, and so this event was look like very interesting for us. Also, we had really good scene during the observation. Here you can see these black bullets. They're taken during the observation. This color one, they are taken from the GRIS header. So this is our observation time actually for the first 3 scans. So first we make 3 scans. Actually, it was my first time, so it was challenging for me. So then we saw, of course, the flare is going, and then also we took another 2 scans. But in this work, in this presentation, I will just concentrate on these 3 scans, which we performed for the start during the event. So I want to say that these 3 scans cover the post-flare phase, then between the 2 flare phase, some more or less quiet phase, and then initial phase of the second flare. So here we just showing the images from the TO, and here is the movie. This is just for comparison that we didn't have a lot of changes in the photosphere. So, and here this white rectangle represents the calcium H line from the HiFi, so it has much more smaller field of view, and the red rectangle represents the GRIS slit scan where we scanning, and we have spectra from there actually. So it is important just to have this, for example, 2 different layers, 2 different lines, even not only 2, much more. Because to define the dynamics between and the transportation of the energy between the layers. So here in the calcium images or movies, we can see this haze-like structure, also some small brightenings, but I mean, this is the chromosphere, so we did not see any changes in the photosphere. So because of these 2 different movies, you can have some small imagination that it's vital important to understand what is happening on upper layer, what is happening in lower layer, how they are connected, and etc. So sorry. It didn't want to go to next slide. I don't know why, but yeah. sorry for that, but I need just switch again. Yeah, now it's moving. Come on. Few technical problems always appear. You can come. So just try to shut it down and not the presentation. I will continue the speaking. So mostly we scanned also with the GRIS. So I wanted to show, but somehow it's stuck. So I'll try to continue without presentation, and maybe sometime after it will rest. I don't know why. So it will switch on again. So then also we try to scan. We switch the near the sunspot because it's important for us, for solar physicists, to have a little bit small in field of view the sunspot because of the to define better these small scale structures which we want to observe in the atmosphere, and then mostly the adaptive optics is using for the to distinguish all this turbulence which appear during the observation in the Earth atmosphere. So for us, it's important to have better define these small scale structures. Also, we used SDO-IM to define what was happening in the upper layers in the corona, but we didn't have much more we only have few of the images. Mostly the SDO is concentrated in big field of view, while the GRIS and HiFi are concentrated much more locally in small scale structures. Should I shut down?
It just froze.
Okay.
I see.
Yeah, okay. Oh, I will shut down and then reconnect it again. So, and mostly during our observation, we define the really strange profiles. So hopefully I can show it. Uh, I I will not go in slideshow. I will just show the profile. So now it's already on. So I think it's better not to go on slideshow because so as I told you, we have the observation from the spacecraft. And mostly we use the spacecraft because to see different extreme ultraviolet images, movies there. So here you can define first two images mostly are photospheric transition regions. Then the helium line here, but this is mostly the transition between the photosphere and the chromosphere and the corona. So all these below three lines are coronal lines. So after the scan the field of view, we have these three scans. So it's from first column and it's from the first scan, second and third, with the different lines on it. So in first line it's the silicon photospheric line. Then we have helium line, chromospheric, which we are interesting much more here. And then all these three are calcium, sodium, and again the calcium are photospheric lines. Possibility to define all these lines together. It's like huge luck in solar physics. I can say this. So as I told you, first from the after the post-flare phase of the first flare, we had such spectra. So the spectra are taken from this black asterisk here on the upper images here. This is the silicon, helium, and calcium. So you can define that in the helium, silicon, we have also the brightening, but there is nothing in the calcium. And this orange profile represents the local quiet sun profile, just to define the differential between the these two profiles to show better that the helium was in emission and it was a little bit redshifted. So this is actually the normal previous works also define this, that during the flare we have emission because of the plasma is heated up and the redshifted because of the plasma from the corona going down in a lower layer. But on the other case, we also have like here the redshift emission, but at the same time nearly we have the emission, but in this spectra we have blue shifted. So now I want to take your attention on these profiles because this is this needs like carefully analyzed, because on the other sense we have in the photospheric line we have some brightening, then in helium of course, but we have nothing in calcium, and on the other side we have such profiles. So we try to carefully analyze this because of course this is something new, but on the other hand definitely this is of the broadening of the helium line. First, because of that we see still absorption in the silicon line. So we all know that the core are generated, line core generated much more higher than the line wings. So, and in this case, we have line core in absorption and then the emission in line wings. So it can be such that we didn't have any brightening, any changes in the lower lines, in the calcium line, for example, here, sodium, also a little bit change here in calcium line, but mostly it didn't change a lot. But then we have change in the silicon line, and of course, some absorption also appear in the helium line. So mostly this is because of the helium is the broader. So because of that, important to analyze these lines together. If we took only, for example, silicon here and see the maps, maybe this will lead some misunderstanding that some event or some hot plasma coming from the photosphere. But also we have the images, the movies from the HiFi DO from the photosphere, so there was no change in the photosphere. But on the other hand, this is challenging to somehow to derive or to describe what was going there, how the structure was created, how the plasma was moving, because nearly the points are near to each other. So if we define these two, red and blue shift, they almost the same time. Of course, there is few seconds of difference. We have upflow and downflow almost the same time. As I told, the difference is few seconds. So, and also this is not only few points which we have seen such emission, but also there are few more. So this is just another example of the line emission. The blue broadening of the helium. So here still the silicon line core are in the absorption. So mostly this is the broadening, and it's so huge that the blue shift almost reached the 120 kilometer per second. So our thought is that the helium overlapping the silicon wing, so then these brightenings also appeared in the maps, but mostly the signals come from the chromospheric layer. Here, just to define, to find the velocities, so the same, we took the same spectra. So here you can see this redshifted emission, the black. This actually during the post-flare phase of the first flare, and the second one is during the initial phase of the second flare. So between we have also profiles. So the difference between these two images nearly 6 minutes. But also all the scans is performed totally 3 minutes took to take the one scan. But the important thing here is that the emission of the helium line was after the flare, first flare, after the maximum. Then it appeared again. The profile became normally, and then it appeared in emission again during the initial phase of the second flare. So there's the same with the blue shift. So blue shift appear nearly nearly the maximum was of the second flare. So as I told, we analyze all these profiles. We are trying to define all the physics, what are going there, dynamics. But of course, we we want to do something to interpret it, but as I told, it's really challenging for us, for solar physicists. But on the other hand, so the in previous works, the redshift were just normally appeared because of the plasma after the flare appeared in the corner. After the flare, it's going down. So this is fine, but we did not find any previous work which describes such blue sheets which we had. So one of the reason on one of the explanation of this can be that the flare during this small C 3.5 flare originate in the chromosphere layer. So then we have this heated up, so we have upflow and blue shifted. And definitely it's not the signal from the photosphere, it's from the chromosphere, because of the helium broadening. What is our future work, what we are going to do? So first we want to synthesize such profiles, at least to make some test model that will describe or maybe just to have some initial guess what is going there, which will in future lead then to also improve the inversion for these special profiles, which really looks strange. So yeah, the next few weeks, which I will be here, mostly with Carlos, with Manolo and Christoph, we will work on it. So then also we want to inverse these profiles, but this is of course our future plans. Because this is challenging. Either we need to change some code, so like it will be challenging for us. But yeah, this is our work. So this is all. So thank you. So I'm open to questions. So please. Thank you.
Okay, are there any questions?
Zurab, the active region and the flat is rather close to the limb. Right?
Yes, yeah, sorry, I forgot to mention. Yeah, we were near the limb. So also this is challenging to describe the situation, the structure, how was going there. So either this redshift, the moving upflow, downflow, it's not the correct guess from us, but yeah.
Yeah, that
This
was
is
my
what-
question. You have red shifts and blue shifts, and the interpretation in terms of upflows and downflows is not direct. Can you use somehow the images, calcium images or SDO images, to track the individual features, just to guess whether you have an upflow or a downflow?
So I found Gong H alpha images. So
Alpha?
yeah,
Complicated.
maybe we can track, but not these small scale structures. I mean, we can track the plasma flow, for example, like you see here in this movie, for example, but small scale structures, it will be challenging.
That's complicated. And another question is, did the magnetic field configuration change?
Actually, no. We didn't see any changes in the. Sorry, here. Okay. yeah, there is not so sorry. I didn't put the this image here, but we have we plot for the same point for the same profiles in all scans. We plot them Stokes V, and we didn't see any changes in the amplitude of the Stokes V. So.
Sorry, by any chance, are you also interested to measure the distribution of magnetic shear before and after the flares? But you have the observation in the link, so I think it's a bit difficult, no? Or do you have any inference magnetic shear distribution changes?
Yeah, we just concentrate on the synthesize such profiles, but of course it will be important also challenge to measure. But yeah, I have no idea how to measure it. So. I mean,
Yeah. So the thing is, I mean, if you have the magnetic field configuration in the photosphere or the chromospheric part, so by taking the temporal distribution of the strength Bx, By, Bz, you can calculate the magnetic shear. I mean, how the loops are sheared before and after the flare.
Yeah,
Why I'm
maybe.
asking
Yeah.
because if you have the I mean, how the post-flare loop after the eruption happens, so how the shear drastically falls down. So do you have any inference from that?
No, I have no information. We didn't did it yet. So, but yeah, this is a good comment. So thanks for advice. Yeah, of course. Yeah. Thanks.
Okay, are there any other questions?
I
Let
mean,
me check online. So Ignacio Morales, do you have any way of predicting the class of an incoming flare before it triggers?
No, because the flares actually, this is like such events that you cannot predict it. So it's sudden appear, and even during the observation, for example, we observed different field of view during our observation. Then we saw the X-ray going up, so we find the field of view, we change the telescope, but before we took this observation, we are observing, we are looking simultaneous field of view which the IRIS spacecraft was stored, but then of course we change, and it's important to understand that yes, we have both spacecraft and the telescope, but the challenge is that in spacecraft, during spacecraft observation, you will just send this information, what field of view you want to observe day before, and with the telescope you can change it like in a minute, for example. So yeah.
So another question, how about Stokes Q and U? Do you see any change before, during, or after the flare?
No, there was not so change. So because of that, I did not put it here in our presentation. But yeah, we didn't see any changes. So even in Stokes V, so the Q and U are much more like not so strong signals.
Okay, thank you. Well, if there are no more questions, then we can thank the speaker again.
Thank you.